these sampling distributions...
The Seattle Epidemiology Research and Information Center, in collaboration with the Department of Veterans Affairs, the VA Employee Education System, and the University of Washington Department of Epidemiology present the 2002 VA Epidemiology Summer Session.
Good day. My name is Gail Reiber. I'm the course director for the summer epidemiology sessions, and I'd like to welcome you to this session. Our faculty is Dr. Marie Diener West. She is a professor of biostatistics at the Bloomberg School of Public Health, Johns Hopkins University. Dr. Diener West has won many awards for her teaching, and we're delighted to have her here today. Her topic today is going to begin with sampling distributions. Dr. West.
Thank you very much. What I'd like to do is actually review something that we had discussed earlier. Yesterday we had looked at elementary probability concepts, we had looked at some probability distributions, and we defined a probability distribution as a description of the probability associated with each possible value that a random variable could take. And remember, a random variable is nothing more than a characteristic that can take on multiple values, like infant birth weight or height or blood pressure. So we had focused, though, yesterday on the normal or Gaussian probability distribution, which is used to describe continuous data. So I just wanted to show you that there are some applets that are available on the web, and these will be posted on the course website. But you can see here a normal probability distribution. It's actually a z. It's a standardized normal distribution because its mean is 0 and its standard deviation is 1. What happens if we shift the mean in location? So if we shift it to the right, all that happens is that this curve just shifts either to the right or the left as we change its mean. So here we have a mean of 2.3, but the standard deviation has remained the same at 1. Well, what happens if we actually take this back to 0, but by going like this, whoops. If we shift this back to a mean of 0 and change the standard deviation. So if I change the standard deviation by increasing it, look what happens to this probability distribution. So in other words, when we have an increased standard deviation, the curve becomes flatter, the probability spreads out across more values, as opposed to if we decrease the standard deviation, we have more probability associated with the values that are nearer the mean and less that are associated with values out in the tail of the distribution. So this is a fun applet to look at to illustrate the differences between means and standard deviations and how they affect the shape and the flatness of the probability distribution. Now there's another one that I'd like to show you, and that one is one that allows you then to look at the area under the curve. So remember, the total probability is equal to 1. What's outlined in red right here is just half the probability under the curve, so 0.5. What's unshaded is also 0.5. And if I wanted to calculate the probability of, say, a z of -2 or something less, I could enter this in and calculate the probability, and you see that probability is exactly what's tabled in the appendix in the book, 0.0228. If I wanted to look at the probability of a z-score of 2 or something less, it's everything that's shaded to the left of 2, which is red, and that probability is 0.9772. By default, what's the probability that z is bigger than 2? 1 minus this, 1 minus 0.02228. Okay, so I thought that it would be good for us to review the characteristics of the normal distribution and to look at how applets can help us visualize changes in the normal distribution as well as associated probabilities. What we'll be looking at today are methods for characterizing how we can make an inference about a population distribution based on just the data from a sample. And so it's here that we're now going to take the concepts that we introduced last time regarding probability and probability distributions to lead into making an inference. So The outline for today is that we'll look at defining sampling distributions and how they help us in the two techniques of statistical inference, estimation, which includes point estimation and confidence interval estimation. We'll spend time talking about what are commonly quoted 95% confidence intervals. We'll also see that there is another distribution of interest to us, a t-distribution, and we'll wrap this all up together in an example and then see as well how sample size is related to estimation. So, what's a sampling distribution? This is probably the most critical concept that forms the underpinning of making statistical inference. And unfortunately, it's one of the most complicated ones too, because of the fact that it's a theoretical distribution. So it's never a distribution that we will build ourselves based on our data. It's a theoretical distribution. And let me see if I can help describe this to you. So a sampling distribution is a theoretical probability distribution of all the possible values that a sample statistic might take if we computed these sample statistics, like a mean, from all possible samples of size n, little n, that are drawn from the same population. So how to make sense of that? Suppose that what we do in practice is we conduct a study. We either aim to have a simple random sample, or we aim to have a sample that is, as far as we can hope, a simple random sample. In other words, a simple random sample is one in which we draw it from a population. The sample is of size little n. We draw it from a population of size big N in such a way that every possible sample of that same size little n has the same probability of being selected. So suppose we had the entire population of 70 students in this class, and suppose we wanted just a sample of size 10. We can imagine throwing 70 numbers into a bag, pulling out 10 numbers as our sample, and then calculating the mean age. Now imagine that if I took a sample and you took a sample and everybody took a sample, and we took all possible samples, of which there are many, 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 and each of us calculated the mean, and then we plotted a histogram of the means. What that is the sampling distribution of the mean. So there are many ways in which a simple random sample could be picked. We just talked about pulling numbers from a hat or from a bag. There are random number tables. There's one in the textbook by Lay. There are computer programs and calculators that generate random numbers that would help us get a random sample. In practice, we don't always have a simple random sample, but we often assume that we do. And our methodology is based on a simple random sample. So if it makes sense, what I just described, we can really think about three distinct distributions. One is, if we had the entire population and we were looking at the ages of the entire population of people in this class, we would have the population distribution. And we could describe the shape, the central tendency, the spread of the population values. What we would have is, if we looked at just a single sample of size 10, we would have the distribution of the sample, and we could describe the shape and the central tendency and the spread of the 10 values that we sampled. The third distribution, though, is this theoretical distribution, the sampling distribution, that describes the shape, the central tendency, and the spread of all of the possible summary values, like the mean, the sample mean, of all possible samples of size n taken from the population. So the first one, the population distribution, is usually one that we have no complete knowledge of. We don't know the entire population. I could say, suppose we took this class, and then we might know the population, but in reality, most of the time, we don't know the full population. What we know is the sample and its characteristics. And if we make some assumptions and try to test a hypothesis, we might be able to describe the sampling distribution in theory. And that's what we'll be developing today. So let's see if I can show you a figure. Suppose we had a population distribution where the mean was mu and the standard deviation was sigma. And suppose then I talked about graphing in a histogram, which then could be approximated by a normal curve. Suppose I talked about graphing the values of the statistic, the summary statistic, such as the sample mean. So if I then graphed this, I would see that the central tendency for all the values of that statistic I could call the mean of those statistics. And the standard deviation of that statistic would be the spread that I would see in the values that it takes. Now, I see a lot of heavy eyelids and some nodding going on right now. And this is a theoretical distribution, so it is a little bit difficult to grasp. But let me try again to say this is the population distribution. This is the distribution of the values of the statistic. So we're going to see that there's a variation on a theme in which the sampling distribution that we're looking at might be the sample mean if we're sampling from a population of continuous values. It might be the sample proportion if we're sampling from a population of dichotomous or binary outcomes such as disease status, disease, non-disease, success or failure, dead or alive. And often this is expanded then if we have two populations and we've taken a sample from each, we may be interested in the difference between two sample means or the difference between two sample proportions. We'll be explaining each of those in turn, but these are the four scenarios. So how can we talk about the sampling distribution of the sample mean? What it is we're indicating that the statistic of interest, the one that we calculate based on our data, is the sample mean. It's the average taken from the sample we've collected. And the sampling distribution then helps us describe the probability or likelihood of every possible sample mean that we would be able to take from, theoretically, if we sampled all possible samples. And as you might imagine, if I took a sample of 10 people in this room and you took a sample of 10 people and somebody else took a sample of 10 people, we would expect most of those means to be close to the true population mean. But just by chance alone, I might have the luck of the draw and I might get a sample that tends to have older students. So I would have an older sample mean. You might take a sample that tends to have younger students and you might have a younger sample mean. But some will have high probability, some will have low, all of them are possible. So let's try to put some numbers to this, and we're going to go back to that simple example we had yesterday of 10 student ages. Those 10 students, remember the true mean, and this is a very small population, big N is equal to 10, but the mean would be 38.3 years and the true population standard deviation was 8.6. That's because we had full knowledge of this population. Now, suppose we were interested in taking a sample of size 4. So what are the possible sample means you could get? Well, we had these ranked here. So look what would happen if we had the luck of the draw and we got the first or the youngest 4 in the sample. The mean of these 4 values is 30.25 years of age. Somebody else might take a sample where by the luck of the draw they got the top 4 years. So the mean there would be 46.75. So this is really the lowest sample mean that you could get with a sample of size 4. This is the oldest or the highest sample mean that you could get of 46.75 with a sample of size 4. What do you expect the typical sample mean to be, the one that has the highest probability? The same as the population mean. So the ones that have the highest probabilities are those that are near the population mean, but we still have a chance, we have some probability of getting a mean that's as low as 30.25 and a mean that's as high as 46.75. Make sense? So what we can describe then are two different distributions. Since we knew in this artificial example, the whole population of 10 ages, we can describe our normally distributed population of ages as saying that 68% of the ages in the population fell within plus or minus sigma years of the true mean, and 95% fell within plus or minus 2 sigma years of the true mean, and 99 fell within plus or minus 3 sigma years of the true mean. The sampling distribution, on the other hand, describes the spread in the values of the possible sample means when we limit ourselves to all possible samples of a particular size, little n. So in this case, when little n is equal to 4, the sample size is equal to 4, the sampling distribution is one that tells us 68% of the mean ages would fall between plus or minus sigma over the square root of n years of the true mean. 95% of them would fall within plus or minus 2 sigma divided by the square root of n years, and 99% fall within plus or minus 3 sigma divided by the square root of n. Now, what do you notice as the difference between the population distribution and the sampling distribution? You notice that there's a square root in the denominator of this standard error or standard deviation. So what this means is that the population distribution describes the spread in the ages. The sampling distribution is going to be more narrow, and depending on the sample size, as the sample size increases, what happens to this term? As n becomes larger, this whole term becomes smaller and the spread becomes less. So if we have a large sample size, we would see that there's not much variability in the values of the possible sample means we might get. With a smaller sample size, there's more variability. So we're going to look actually at a simulation of a sampling distribution to put this into place as well. But if I back you up to slide 10, if we have sampled from a population that's normally distributed, then the sampling distribution of these sample means is also going to be normally distributed. Now, some of you might ask, what happens if the population distribution isn't normally distributed? Wonder if it's skewed in some way or takes on some other form. It's not a symmetric bell-shaped curve. Well, no need to fear, because there's something known as the central limit theorem, which says even if you have a population of non-normally distributed observations, the sampling distribution of the sample mean will still be approximately normal with a mean, so a mean of the means, a mean of the sample means that's equal to the true population mean, and a standard deviation that's based on the population standard deviation divided by the square root of the sample size, as long as the sample size is large. Another question is, well, how large is large? Large actually only needs to be 25 or 30. So as long as the sample size is 25 or 30, we'd have the situation like we see here. On the top panel, we'd look at serum cholesterol values. Is it normally distributed? It's pretty skewed. It's skewed to the right. We see this bulk of observations are towards the left with a tail to the right. So the population distribution is skewed, but if the sample size is at least 25, what we would see is that if we looked at a histogram of all of the possible sample means, so this should actually say X bar for sample mean in the bottom panel. This should really say X bar. Then the spread in all of the possible sample means will be dependent on the population standard deviation sigma divided by the square root of the sample size. What's the mean of the means? So in other words, I know I'm using the word mean a lot, but what's the average value of all of the sample means that we could possibly take? What's the average value? The average value is the same as the true population mean. So we see there are many values of the sample means that are possible around the true value of mu, but we also see that some sample means might be out here in the far right tail, some might be out here in the far left tail. They're all possible, but the probability is less. So we're going to see that sampling distributions actually help us out quite a bit with estimation and hypothesis testing. And so I'd like to show you this. I think you can see that we have a parent population. Here's a population. It's a nice symmetric bell-shaped curve. And we see here that the mean of the population is 16. The standard deviation is 5. Now suppose I was interested in looking at a sample. So I'm sampling from this population. And I have just a sample of size 5. Did you see what happened? I'll do that again. I'm going to take a sample of size 5, and the second panel shows the 5 observations that came down from this population. It's a random sample of size 5. What's the mean of the sample? 15.54. How does it compare to the true mean? Pretty close. What do we see about the spread in the sample? It's a little smaller, but it's only a sample of size 5. I could have, suppose I clear this and I look at a sample of size 25. Here's the sample of size 25. What's the mean? 16.8. How does it compare to the true mean? Pretty close. And we see the spread, again, is similar to what it is in the parent population. Now, suppose I clear these and I will look at, in the third panel, all of the possible means, the summary statistics that we could get if we took 10,000 samples of size 5, and then if I ask also to look at all the possible means that I would get if I took a sample of size 25, and then I hit 10,000 samples. So this is a simulation that's going on. And now what I have in blue in these bottom panels are actually what are known as the sampling distributions. So this is the distribution of the sample means. It's all the values of the sample means that we would get by taking 10,000 samples of size 5. These are the values of the sample means that we would get by taking 10,000 samples of size 25. What do you notice about the mean of the means? Similar to the population mean. So one is 15.99, the other one is also, the true mean is 16. So we're seeing that the central tendency in these means is the same as the population mean. What do you notice about the spread? So there's actually more spread in the values of the means when our sample size is only 5. When our sample size is 25, there's less spread. There's higher probability associated with means that are close to the same value as the true population mean. So what are the differences in the distributions here? This one was the population. If we had cleared this and we just took one sample, this is the distribution of the sample. And what we had on the bottom two were the distributions of the means. Does that make sense? Now, what would happen if I changed this parent population and made it very skewed? What do you expect would happen? I'll let you see. So I'm going to still keep a sample size of 5, a sample size of 25, and I'm going to look at 10,000 samples. So what we see is that actually the mean of 5.92, we still have a similar mean in these sampling distributions, the mean of the means, but what happens to the spread? When the sample size is only 5, this is a little bit skewed. It looks more similar to the parent population. When we actually have a sample size of 25 or something bigger, this sampling distribution becomes more symmetric and bell-shaped. So this is how the central limit theorem holds, that when the sample size is large enough, it doesn't matter what this what the parent population looks like. The sampling distribution will still be approximately bell-shaped or normal. And so we're going to be basing our theory for both estimation and inference and hypothesis testing on this sampling distribution being approximately normal. So what we're going to spend the next half an hour on is looking at estimation. What do we mean by estimation? Remember yesterday I said that the statistic is the estimate of the population parameter. It's what we derive from the sample that we've taken. And we can define point estimation as the single value that we might get from our sample. So a sample statistic is an estimator of the population parameter. The value that we would get is the estimate. So if I'm estimating the mean age based on a sample, the estimator is the sample mean at x bar. The estimate that I would get may be 32.3 based on the sample that I've taken. On the other hand, an interval estimate is not just a single value. We would take the point estimate that we derive from our sample and express it as an interval, which expresses the certainty or the uncertainty or variability associated with the estimate. So it's influenced by the sample size, it's influenced by the variability in the population, and we'll see how that comes into play. So the point estimate is the best estimate that we have of the true population parameter based on our data. So when we perform a study and have a single sample, our best guess at the truth is this single value of a mean or a proportion that we've calculated from the sample data. An interval estimate, as I said, is an interval of values that we expect to be consistent with the truth based on what we have calculated from our sample. And an interval estimate goes by the other name of confidence interval. So, as I said, for a single sample, depending on whether we have continuous data or dichotomous data, the sample mean may be the best estimate of the population, the true but unknown population mean, and the sample proportion is the best estimate of the true but unknown population proportion. And we will be developing the notions as well that when we're interested in comparing two groups, such as drug A versus drug R, if we have continuous data, such as mean times to response, then the difference between two sample means, in which we've taken samples independently from one population and another, gives us the best estimate of the true difference in the two population means. Whereas if we have a binary outcome, the difference between two sample proportions gives us the best estimate of the true difference between two population proportions. Make sense? So we'll be looking at examples of these, but it's all a variation on the same theme, looking at either one sample or two samples from two independent populations, either continuous data or dichotomous data. So how would we construct a confidence interval based on the point estimate that we calculate from the sample data? By definition, a 95% confidence interval for the true population parameter takes the value of the sample statistic that we calculate from our sample and forms an interval around it by adding and subtracting the tabled z value that corresponds to an alpha of 0.05, meaning 5% probability out in the tail of the distribution corresponds to 95% probability in the middle of the distribution. We take the tabled z times the standard error that corresponds to the sample statistic of interest. So there are two ways of thinking about a confidence interval. Suppose that we actually took all possible samples that we could of a certain sample size n, and we calculated the mean, and we formed this interval around the sample mean, and then we plotted them. So we don't do this in practice, but in theory, think if that's what you did. You took all the possible sample means, you formed these intervals around them. What we would see is that 95% of these intervals, meaning 95 out of 100, would actually include the true population mean. What happens to the other 5%? They don't. They don't include. They either fall to one side or the other of the true population mean. Does that mean we haven't sampled from that population? No, it just means that 95% of the time it will contain the truth. 5% of the time we have drawn samples in which their confidence intervals would not include the true value of the population mean, even though we've sampled from that population. So this is an underlying interpretation of a confidence interval. It's, as I said, not what we do in practice. In practice, we've conducted one study. We have one we have one mean, we calculate a confidence interval based on that sample mean, and we're able to make the statement that we're 95% confident that this interval that we constructed based on the sample data, that this interval contains the true population mean. So we form an interval based on our data, and now that we have an interval of values that should be consistent with the truth. So for a single sample, sampling from one population, a 95% confidence interval for a population mean is based on taking the sample mean that we calculate from our data, adding and subtracting 1.96, because that's the z that corresponds to 0.05 divided into 2 tails, so 0.05 divided by 2 to give us 95% confidence, times the standard error of the mean, which is sigma over the square root of n. So remember, we said that the spread in the sample means was given by taking the population standard deviation sigma and dividing it by the square root of the sample size. So the larger the sample, what happens to the width of this confidence interval? Becomes smaller and smaller. So as n increases, the confidence interval becomes smaller. As n decreases, the confidence interval becomes bigger. So here's a diagram of if we indeed had sampled from a population where the mean, the true population mean was mu, we can think of each of us taking a sample of size n, getting a sample mean, such as the one I'm highlighting here, forming an interval around it by adding and subtracting 1.96 times sigma over the square root of n, and somebody else might get a mean that's here, form an interval. So in fact, what we would see is that some of these intervals overlap the true mean, others don't. And in the long run, 95 out of 100 of them will overlap this true mean. So I am going to take you to just one final simulation today, and that's one with confidence intervals. So if I take you to this, what you see here is a population that has a true mean of 50 and a standard deviation of 10. And I'm going to take a sample size of 10, and this will now give us 100 samples. So think of taking a population, 100 samples are taken, independent samples, the means are calculated, and confidence intervals are derived. That's what this is doing. And what we see here are in the yellow, we have the confidence intervals, and the blue is, the yellow is the 95% confidence interval. The blue is the 99% confidence interval. We'll talk more about this. But what you see is that most of these confidence intervals overlap the true value of 50. Some of them don't, which we would see by the fact that they're outlined in a different color. What happens if I increase the sample size to 20 and sampled? We see that the confidence interval width decreases. So, and if we looked at the cumulative result that's here, we would see that out of the samples of 100 that were taken, 185 contained the true mean of 50, 15 did not contain the true mean. So in fact, the proportion that was contained was about 92.5, almost 95. The reason it's not exactly 95 is because this is just 200 of the possible samples, not all possible samples. Okay. So which one of these, though, will I have when I do my study? Don't know, but only one of them. Only one of them. Okay. Okay, so we talked about setting up a confidence interval based on the sample value, adding and subtracting a z times sigma over the square root of n. I'm going to introduce one more distribution. Rather than the z, the t distribution is an alternative distribution that's used when the population standard deviation, sigma, isn't known. So if we don't know the true population mean, we're most likely not going to know the true population standard deviation. So most of the time, we would like to estimate, based on our data, the standard deviation as well. So the t distribution is similar to a z. It's symmetric. its mean is equal to its median is equal to its mode. Again, the possible values of t range from negative infinity to positive infinity. The difference is that it's actually a family of distributions that is determined by the sample size minus 1. So the n minus 1 is referred to as the degrees of freedom, and it's all dependent on the sample size minus 1. It's decreased a bit because of our uncertainty regarding the true population parameters. What is true is that this distribution, the t distribution, becomes fairly like a z as the sample size increases. So how would this change our confidence interval construction? The way it would change it is that when we don't know the truth about the population standard deviation, we'd use our best guess, which is S, the sample standard deviation that we can calculate from our data. So we'd still form the confidence interval by taking the sample mean, plus or minus, but now instead of using a z statistic, we would use a t, still corresponding to an alpha of 0.05, split in two tails of the distribution, but now the standard error is going to be formulated by S divided by the square root of n, where we're using S as an estimate of the true population standard deviation. So let's look at an example to make some sense of this. So what we had was this population of 10 students where the true mean was 38.3 years, the standard deviation was 8.6 years. So this is a case where we truly know the population standard deviation. So suppose we took a sample of size 4, and we have 4 observations. We can calculate the mean as 40.75 years. We can also calculate the standard deviation based on those 4 observations as 9.2 years. The confidence interval would be based on taking the sample mean plus or minus a t times s over the square root of n if we didn't know the population standard deviation. So let me take you back to that previous slide. So we know that the true population standard deviation was 8.6. Pretend to erase this knowledge. So if you have no knowledge of the population and we take a sample of size 4, the only knowledge we have now is that of the sample. So the sample size was 4, the sample mean is 40.75, the sample standard deviation is 9.2. Looking back, is it a good estimate of the population standard deviation? Not bad. We usually can't assess that, but based on the fact that we know the truth here, it's not a bad estimate. So the confidence interval is going to be based on taking the mean plus or minus the t value that we get that looks at 0.05 split in 2 tails of the distribution, but with n minus 1, or 3 degrees of freedom, times s over the square root of n. So we would look in the table that's in the appendix in the book, and we would see that when n minus 1 is 3 degrees of freedom, the corresponding t, where we have 0.05 split in 2 tails of the distribution, is 3.182. So you can look that up on your own later. But how does that change this interval? We take the sample mean of 40.75, add and subtract the t times s over the square root of n of 9.2 divided by the square root of 4, and we would get an interval that ranges from 26 up to 55 years. So based on our sample of size 4, what can we conclude? You can conclude that this is a range of values from 26 up to 55 of years of age that are consistent with the truth. We don't know where the true mean falls. Well, we actually do because we said this was a population of size 10. But what we can say based on our data is that I'm 95% confident that this interval that ranges from 26 to 55 years contains the true population mean. Now, we do have the luxury, so let's go back. What was the true mean? 38.3. Is it contained in that interval? Yes. Yes. So, but we only knew that because we knew the population. Most of the time, we don't have that knowledge. But at least this interval gives us a range of values that we could say the mean could be as low as 26, the mean could be as high as 55. We're 95% confident that somewhere that this interval in this range contains the truth. Okay, so let's just again talk about what happens to this confidence interval as the sample size increases. Because the denominator of the standard error then increases, this quantity decreases and the confidence interval becomes narrower. Let's look at another example. Suppose we looked at the birth weight example and we have no knowledge of the population. All that we know is we've taken a sample of size 25 and we calculated a sample mean weight of 2,500 grams, a standard deviation of 900 grams. Where did these come from? Just from the sample of size 25. So based on the sample then, the 95% confidence interval takes the mean plus or minus the t that corresponds to n minus 1 or 24 degrees of freedom times the standard error of the mean, which is s over the square root of n. So again, I'd have to look up in the t-table with 24 degrees of freedom with alpha of 0.05 split into two tails and see that the t-value is 2.064. Now, with a sample size of 25, if I didn't have access to my t-table, what could I use instead? I could use the z. So I could use the z of 1.96, or I could round 1.96 to 2. And I wouldn't go far off because the t of 2.064 that corresponds to 24 degrees of freedom is not very different. So let's use the exact t, though. So I take the mean weight of 2,500, add and subtract 2.064 times s over the square root of n. If I go through the math, I get an interval in which I can say I'm 95% confident that this interval that ranges from 2128 grams up to 2871 contains the true population mean birth weight of the population that I've sampled from. So it places some bounds on our certainty about the population values based on all that we know, which is the data from the sample. Okay. Any questions up to this point?
Is the degree of freedom always the sample size minus 1?
The degrees of freedom are always for the single sample case, the sample size minus 1. Yes.
If you have if you don't have access to the t-table and you use the z value instead, will that overestimate or under? I'm just sort of
right. So this
how does that affect your
right? So let's go back and look at that. This was a very good question. The question was: suppose you don't have access to the t-table and you used a z instead. So we can look at this formulation as taking the mean plus or minus the t. Now what we will see is that here's the t distribution, and what we have here, if I press overlay the standard normal, is the normal distribution. So the t distribution has thicker tails and less probability in the middle of the distribution. If we change the degrees of freedom, right now this is showing degrees of freedom of 1 for the black outlined t distribution. What we'll see is that as the degrees of freedom increase, so here, well, I increased that very quickly, but from 1 up to 4, up to 6, up to 11, so that actually by the time we get up to around 20, 24, 25, the z is the same as the t. So the only time that this really affects us very much is when the sample size is very, very small. So for most practical purposes, the t value is the same as the z, and if we used a z instead of the t, we would still have a confidence interval which is about the same width. Otherwise, when the sample size is small, t is always bigger than z, so if we used a z, we would be underestimating the width of the confidence interval. Well, we have set up then the general form for a single sample confidence interval when we have continuous data and we're calculating a mean based on the continuous data that we've sampled. We can easily expand that to a 95% confidence interval for a population proportion based on the proportion we calculate from the sample. So again, we would take the sample statistic. Now it's the sample proportion that I'm labeling as p hat. The hat means it's an estimate based on the sample, plus or minus the z that I get of 1.96 that corresponds to an alpha of 0.05 split in 2 tails times the standard error that's defined as the square root of p hat q hat over n. So based on my sample, if I've calculated a proportion having a certain characteristic that's considered p hat, then q hat is the proportion without the characteristic. It's 1 minus it. Let's look at an example to make sense of this. So if I took a sample of size 4, again from the population of interest, but wonder if what I was interested in was not mean age, but I was interested in the proportion of the sample that's greater than age 40, what I would see is that 3 of those 4 are greater than age 40, which is a sample proportion of 0.75. So p hat would be 0.75, and q hat would be 1 minus that, which is 0.25. So now the confidence interval for the true population proportion that we don't know but would like to gain some knowledge of would take the sample proportion of 0.75 plus or minus 1.96 times the square root of p hat q hat divided by n, which is 0.75 times 0.25 divided by 4. If I go through the math, I would see that I get a confidence interval that ranges from 0.33 up to 1.17. But can proportions be greater than 1? No. So I would consider this confidence interval to be bounded by 1. But I'd be able to say I'm 95% confident that this interval that ranges from 33% up to 100% contains the true proportion of individuals in this population who are greater than age 40. Okay, so a simple extension using the same rationale for proportions. So in the next 10 minutes, although we're going to spend much more time on sample size later in the course, it seemed an appropriate time, since we just developed confidence intervals, to see how sample size relates to confidence interval construction and estimation. So if we were only interested in the precision of an estimate, in other words, if we were interested in performing a study and we'd like at the end of the day to have a fairly narrow confidence interval when we write up our results, what we could do up front is specify the width of the confidence interval that we'd like to have, either one that's in terms of plus or minus a certain number of years or plus or minus a certain percentage point. We'd make some assumption about the standard deviation based on previous knowledge, either from the literature or from pilot studies, and then solve for the sample size before conducting the study. So suppose that I really wanted in a population to estimate the true population mean age to within plus or minus 5 years. And what I would do is I'd specify the width of the confidence interval as being plus or minus 5, in other words, a width of 10 years. I'd make some assumption about the standard deviation of age in the population. Maybe I could base it on a sigma of 10 years based on some previous study, and I'd solve for n. So remember that the formulation for the confidence interval was I took the sample mean, added and subtracted z times sigma over the square root of n. So in fact, the width of the confidence interval is only influenced by z times sigma over the square root of n. In other words, since it's plus or minus z times sigma over the square root of n, what's the width of the confidence interval? The width of the confidence interval that I'm interested in is 10, but half the width of the confidence interval is just 5. So plus or minus z times sigma over n would have given me 2 times 5, which is a width of 10. But I can just set 5, half the width of the confidence interval, equal to z, 1.96 times sigma over the square root of n. Does that make sense? And if I go through a little bit of algebraic manipulation, just a little, I could solve for n by moving it into the other side in the numerator, and I would see that solving for n, I would have 1.96 squared times 10 squared over 5 squared. Why is it 10 squared? Sigma was 10, so I've plugged in sigma of 10, and I would see that I'd need about 15.4, but I'd round that up to 16 individuals. So I'd need a sample size of 16 in order to estimate the true mean age to within plus or minus 5 years. Make sense? Now, what if I wanted to estimate the true mean age to within plus or minus 2 years? In other words, an interval of only 4 years in width. I'd set 1.96 sigma over the square root of n equal to 2, solve for n, and I would see that now instead of 5 in the denominator, I would have had 2. So what happens to the sample size? It becomes much bigger. Okay. And I could do the same if I was interested in proportions. Suppose I still was interested in the proportion over age 40, and I wanted to estimate that proportion to within plus or minus 3%. Then I'd specify the width of the confidence interval as being plus or minus 0.03. I'd make some assumption about the true population proportion. And again, if I had some previous pilot data or a previous study, I could make an estimate. Or I could be the most conservative. It would be the one that would maximize my sample size if I used p equals q equals 0.5. If I recalled that the confidence interval was equal to p hat plus or minus 1.96 times the square root of pq over n, I'd set 0.03 because that's half the width of the confidence interval. I'd set that equal to 1.96 times the square root of p times q over n. Again, a little bit of algebra, and if I solved for n, I'd get 1,067. So I would actually need a fairly large sample to estimate the true population proportion to within plus or minus 3%. In other words, the width of the confidence interval would only be 6%, a fairly narrow range. Okay, so what we have done is we've taken the knowledge that we had of probability distributions, in particular the normal probability distribution. We've extended it to a discussion about theoretical sampling distributions that give us a theoretical description of the probability of all possible sample means that we might get when we sample from a population with a given theoretical population mean, or any other statistics. So the common summary statistics that can be described by sampling distributions are the sample mean, the sample proportion from two populations, sampling from two populations with two samples, the difference between sample means, or the difference between sample proportions. We stuck with just a single sample from a single population today, but looked at both the point estimates and confidence interval estimates that we could calculate based on a single sample, either looking at sample means or sample proportions, and then we finished by looking at how sample size estimates are related to the precision of a confidence interval derivation. So we've gone through then just the beginning of setting up estimation and inference for a single population. We'll continue this next time by expanding it to two samples from two independent populations. But I do think we have a few minutes for questions right now.
Just out of curiosity, why don't we use a 99% confidence interval rather than 95%?
Okay, well, this was a very good question. The question was, why not use a 99% confidence interval rather than a 95? Convention has been to look at 95% confidence intervals. One would say that, yes, 99% would give you more confidence. One would be able to make the statement, I'm 99% confident that this interval contains the true but unknown value. But what happens as you increase the confidence to the width of the interval? So you have a much wider interval. So in fact, if you increase from a 95 to a 99% interval, the interval becomes much wider. You have more confidence, but it's a much wider range of values. If you decreased from a 95 to a 90%, you'd have a much more narrow interval, but less confidence. So if you have a large enough sample size in which you could actually construct a 99% one, you would have more confidence in that interval. But convention has that typically 95% is used.